Okay, folks, so I want to look at this function right here. It's sort of an unusual function, h of x. And h of x is defined to be the difference between f of x and this expression here. First thing I want you to do is pause the video and see if this expression right here looks familiar to you. I'll give you a hint. Look for where the variable is and see if you can figure out what type of expression that is. So pause the video and just think about this for a second. So this equation right here we'll look at in just a moment. But let's go ahead and put some stipulations on f. Let's go ahead and assume f is continuous on the interval from a to b, and f is differentiable on the interior of that interval. Okay. So let's go ahead and give ourselves a graph of such an f. Let's see here. We'd have, here's our axes, and maybe here is A, and here is B. Maybe here I've got f of A, and then maybe up here we've got f of B, and maybe this is our function. Maybe this is our function right here. Okay. So here we've got this function f of x. It's continuous, it's differentiable on the interior, it's continuous on the endpoints, on this closed bounded interval. And so what I'd like to do is I'd like to think about the secant line connecting the two endpoints. Oops, that's not very pretty. Let's look at the secant line connecting those two endpoints. Okay. We can pretend that's straight for just a second. So what would be the equation of the secant line? Well, the equation of any line can be given in point-slope form, where we have y minus y1 is equal to m times x minus x1. And since these are points on a function, let's go ahead and pick the x value a. We could write this as y minus f of a is equal to m times x minus a. And what would be the slope of this line? Well, we might know what it is, but we could also calculate it using just the slope formula. So notice that the slope is the difference between the two y values, f of b minus f of a, all over the difference between the two x values, b minus a. This is the slope of this green secant line here. Let's see if we can clean that up a little bit. Okay. So this is the slope of that line. So what's the equation of this line? The equation of this line is y is equal to the slope, which we just computed to be f of b minus f of a, all over b minus a, that's the slope, times x minus a, and then we can add this f of a term over to the other side. And so this is this green line right here, given in this formula, is the equation of the secant line connecting these two endpoints. And that's precisely what I've written up here. Okay, so now that we've explored this a little bit, we know that the blue function is given by f of x, and then the green secant line is given by this expression right here. Okay, so just be careful here. This is just m times x minus a plus f of a, right, where that's just the slope of that secant line. It's a large-looking expression. Okay. But I still ask the question now, what is h of x? So I'd like you to pause the video and think for a minute and see if you can figure out what h of x is here. Pause the video. So what is h of x? Well, h of x is said to be the difference between the f of x value and the secant line value. So visually, we can imagine h of x as being this distance right here. If this was an x coordinate, h of x is the difference between the f of x value and the secant line value at that same point. So that's maybe for one x value, maybe let's call that x1, I guess. Okay, if we did it for a different x value, maybe there's x2, what would h of x2 be? H of x2 would be this distance right here. So h of x is a function that for any x coordinate between a and b tells you the difference between, and by difference I mean the difference between the blue line and the green line at that given x value. Okay. So let's see what we can notice about this function. It's a really interesting function. The first thing we notice is that h of a is what? Well, h of a would be f of a minus f of b minus f of a all over b minus a times a minus a plus f of a. And if we clean this up, what happens? Well, notice that for this large expression right here, we just simply have a minus a, so this whole expression here is 0. And so that would clean up to be f of a minus 0 minus f of a, which gives us 0. Now, I want you to, we just computed that algebraically. We just showed that h of a comes out to be 0. But look at the picture. Convince yourself that h of a is 0 as well. Let's see if we can figure that out. What does h do? For any given x value, h measures the height or the distance between the blue line and the green line. Well, what is the distance between the blue line and the green line at x equals a? Well, they're at the same point, so their distance should be 0. Similarly, h of b, we expect that to be 0 as well. How come? Because that's the distance between the blue line and the green line, and at the endpoints, they coincide with one another. Okay? So, h of b, then, let's do it algebraically, would be f of b minus bracket f of b minus f of a all over b minus a, and then in place of x here, in this crazy function, in place of x here, we're going to replace that with b. So we've got b minus a plus f of a. And what do we notice happens? Well, first of all, we notice that we can cancel these b minus a factors. Okay. So what does that give us? That gives us f of b minus, those cancel, so we'd have minus f of b plus f of a. And if I distribute this negative sign also over here, we'd have minus f of a. So we're left with f of b minus f of b, that's 0, and f of a minus f of a, that's 0. And so we find that h of b is also equal to 0. That's not really that unusual. That's exactly what we expected it to be, because h is supposed to measure the distance between the blue line and the green line at any particular x value. And at the two endpoints, those two agree with one another. Okay? So why are we studying this function? Well, we just did the proof for Rolle's theorem, and in the proof of Rolle's theorem, we said we were impose some stipulations on a function, and we were going to require that the two endpoints were equal to one another. Well, that doesn't happen with a whole lot of functions, but notice that for this function right here, h of x, when I evaluated h of a, I got 0, and when I evaluated h of b, I also got 0. So the two endpoints agreed with one another. In the proof of the mean value theorem, which we'll do at the end of the next class, we're going to use this exact function, and we're going to apply Rolle's theorem on it in order to prove the mean value theorem. So I just wanted to give you a chance to study this function and get familiar with it, and then we will use it in our proof of the mean value theorem. Let me know if you have any questions.